name is Zach Allen, and today we are going to be learning about perpendicular and parallel forces and the momentum principle, and how it relates to this specific problem. Today we're actually going to be learning, looking at Python, and we're going to try to figure out the mass of a black hole, do the motion of an orbiting star, and then we're going to explain the motion of the star through the momentum principle. And here I have the initial values of the system, star mass, delta t, and the black hole position. So if we go to Python, we have the initial values right here, just a system and delta t. And down at the bottom, I decided to put the gravitational force equation in, and I arranged it so I can find specifically the mass. And here's a constant g. I set g equal to 6.6 times 10 to the negative 11th, and I solved it using magnitude of the F net times magnitude position of the black hole minus magnitude of star position squared over g times star mass. And if I run this, you can see the model, and notice that early around this area the arrows got bigger, and I'll go back and talk about that after we look at the mass of the black hole, which is 1.95 times 10 to the 31st. Okay, so I mentioned a few seconds ago about the arrows getting bigger, and that is due to the force of the black hole on the star. And those arrows represent dp dt and dp dt perpendicular. And you saw that the red arrow moved along as a star moved along, that was a representation of dp dt perpendicular. And what these are very important, because the sum of the perpendicular and parallel force F net is equal to the total F net of the system. And the difference between dp dt and F net, they have the same values, true, but the only difference is that dp dt can be observed, and F net is just something that we know is there, causing our observation. And so what if the black hole was what if there was another black hole replacing the black hole we have here at the same position, and we try to figure out if there would be anything changed about the mass or anything else that defined the black hole. If we did have another black hole at the same position, you wouldn't really be able to tell if the mass of the black hole were different from the original one. Therefore, you could say that the data goes unchanged, and you would have the same mass of the mass of the black hole would be the same. But just so far from this, it seems like that the black hole mass wouldn't change. Thank you for listening. I hope you learned something today, and I hope you all have a great day.